So you can see here, chapter 2 is about matter and the atomic structure. Okay, so let's see 2.1, basic concept of matter. So meaning of matter. So number 1, matter is any substance which has mass and occupies space. Okay, so when you look at these definitions, so I'm going to give you 3 examples at the same time to let you get the idea. So metals, for example, solid is a metal, liquid is also metal, and then gas is also metal. So solid, liquid, gas. So they have mass, they occupy space. Okay, now let's continue. Number 2, metal consists of particles that are tiny and discrete. So tiny means small, discrete means one by one. For example, you can see solid. The particles are one particle here, and one particle here, and one particle here. They are one by one. Okay, so we call that discrete. If they are not discrete, they may like join up. You know, like discrete is like this. If they are not discrete, maybe they join up already. They join up. 2 particles join up, then they are not discrete. Okay, so discrete must be one by one. So number 3, air. So you know air is gas. Water is liquid. Soil, plants, animals, and humans are examples of matter. So solid. So gas, liquid, solid, they are matter. Number 4, all physical objects are metal. So physical objects, something that you can see. Okay, solid, liquid, gas again. Changes in the states of metal. So number 1, you can see metal exists in 3 physical states, namely solid, liquid, and gases. So solid, liquid, and gases, they are known as the 3 physical states of metal. Physical state. So when we say physical, that means you can seal it, for example. Okay, so you can see it is solid, you can see it is liquid, you can see it is gas. Okay, you can seal it. So number 3, table 2.1 shows the property of matter in the solid, liquid, and gas states. So we look at the table. Okay, so you can see kind of basic, you know. So solid, the particles are very close to each other, so we call it closely packed and in an orderly manner. So you can see they're arranged in order. Liquid particles are closely packed, orderly, but not in manner. So they are close, but they are not arranged properly in orderly. Okay, they are not arranged in manner. Okay, not in manner. So that means they don't arrange properly. Particles are disordered and very far apart from each other. So this happens to gas. They don't stick to each other. They are like one by one. Okay, so not like liquid. You see liquid that stick to each other. They are not. They are having a bit of space. But this one, they don't stick to each other at all. Movement of particles. Particles only vibrate at fixed position, so you should expect they vibrate. Particles move randomly, slowly, and constantly collide against each other. So that means they move in all directions, they move slowly, they collide with each other because they are near to each other. Particles move randomly and rapidly in all directions and collide against each other. So that means this one they move faster, they move rapidly also, they move in all directions and then they collide. Kind of similar with this. It's just that this is slowly, this is rapidly. That means this is slow, this is fast. Force of attractions, you can say this is strong, so that's why they are so close to each other and they are arranged in order, arranged in manner. And then moderate, attraction is moderate, the attraction is weak. Kinetic energy, this is low, that means they vibrate only, they move a little bit only. Moderate, they move more compared to the solid. high, that means they move very fast. Okay, now let's move on the next page. So on this page you can see number 3, heat is a form of energy. Okay, so we talk about heat in a sudden because now we are going to heat up the solid to liquid. To heat up the liquid to gas, we are going to heat. So that means when you heat up, you are supplying energy to the particles. So a change in temperature changes the movement and energy of particles in matter. So that means you heat it up, then they move faster, and then they have more energy. Okay, the particles have more energy. So thus, changes in the states of matter can occur through heating or cooling processes. So you want to change the state, of course, it's not just heating, you can cool it down also. Okay, so that is also the change in the state, the physical state of matter. So this takes place when heat energy is absorbed. Heat energy is absorbed when you heat it up, and heat energy is released when you cool it down. So the changes in the states of matter include melting. So melting is solid to liquid. And then freezing. Freezing is liquid to solid. Boiling or evaporation. So both of these are liquid to gas. Condensation. Condensation is gas to liquid. Sublimation. Sublimation is solid to gas. And then the last one is deposition. Deposition, as you can see in the diagram down here, deposition is gas back to solid. Deposition is written here. So it's the opposite of sublimation. Okay. Now number 6, when heat is applied, the kinetic energy of the particles increases. So you know, you heat it up, they have more kinetic energy. And the particle move at a higher speed. So that means they move faster and faster. Thus, changes in the states of matter can occur through heating or cooling. Okay, so you heat it up, they change in physical state. You cool it down, they change in physical state. This is when the heat energy is absorbed or released. Again, heating make energy absorb. Cooling make energy release. So basic thing lah. Now let's continue. Okay, let's see number 8. Table 2.2 shows a brief explanations on changes in states of matter. So first we have melting. Melting is where solid change to solid change to liquid. So when heated, heat energy is absorbed by the particles, by the solid particles, and the solid particles vibrate faster. The particles have more heat energy to overcome the force of attraction between them. You know, solid has the strongest force of attraction. Now they use the heat energy that they get to break down the force of attraction. Freezing, liquid to solid. When cold, the liquid particles lose heat energy and move slower. The particles slow down that their force of attraction attracts the particle into fixed positions as a solid. So they slow down, they form the forces of attractions between the particles, then they arrange themselves in orderly manner, then they become solid. Okay, now let's see here. Boiling or evaporation. It is where liquid change to gas. So when heated, heat energy is absorbed and the liquid particle move faster. The force of attraction between the particle is overcome. So again, they break down more force of attraction when boiling and evaporation happens. So you see, force of attraction is broken down in two situations. The first situation is during melting, force of attraction is broken, and then during boiling or evaporations, force of attraction is broken again. Yeah, so that's why when they become gas, there are not much force of attractions between them. Okay, so let's continue with this part. Okay. So this part we have condensations. So condensation is where gas changes to liquid. Okay, so this happens when cooling happens. So when cooled, the gas particle lose heat energy and move slower. Then they form force of attraction. A stronger force of attraction between the particles attracts them closer to each other. So they are slowing down, then they form forces of attractions, and then they become liquid. Deposition is where gas changes to solid. This is the opposite of sublimation. So when cold, the gas particle lose heat energy and move slower. The particles are attracted closer to each other by the stronger force of attraction between them. So example, iodine. Iodine will go through deposition. Iodine. Okay. Beside iodine, the dry ice. Dry ice will go through deposition also. That means from dry ice it become gas, from gas it become dry ice, the solid. Iodine also, from iodine solid it become iodine vapor, and iodine vapor can change back to iodine solid. So they don't become liquid. Okay, now you see sublimations. Sublimation is solid to gas. When heated, the solid particles obtain more heat energy and move faster. The particles are separated from the solid lattice and becomes free, so they become gas straight away. Okay, so finish the first part. Okay, now let's see this. Okay, from this point, you can see they start going slowly into the chemistry. Okay, so it's more and more chemistry. So you can see elements coming, and then a lot of symbol that represent the elements. Okay, so let's see, atoms, molecules, and ions. Okay, so matter can be classified into elements and compounds. So you see just now I said there are three physical states for matter, which is solid, liquid, gas. So this is the second way to understand matter. Matter can be element, can be compounds. So what is elements? Elements is like they are made of one type of things. Let's say, for example, let's say a piece of iron. It is made of iron only, so we call it elements. Compound is like they make from more than one element. For example, carbon dioxide. Carbon dioxide is made of carbon and oxygen, so it's compound. So you can see here, compound. So H2O, made of hydrogen and oxygen, so compound. Elements, right, must be only one types of elements, only one types of thing. So for example, only carbon. Diamond is made of carbon only. Diamond. Okay, so diamond is the example of element. Hydrogen, you can see here, hydrogen, this is a gas. So hydrogen is just made of H only, made of hydrogens only. So this is also element. Compound, you can see compound made of more than one element. So it's made of hydrogen and oxygen, made of potassium and oxygen. Okay, so we will see it in details. So let's see the information here. Particles in elements consist of atoms or molecules. So it can be atom, it can be molecule. So the difference between atom and molecule is atom is just one. Okay, just one. Molecule is like there are more than one. The same type of element but more than one. H2, more example, let's say O2, let's say N2. So these are elements under the molecule. So there are more than one. Okay, so like ozone O3. Okay, so can be 3 also, you know. You may also see like P4, S6. So there are 4 P is phosphorus, 4 phosphorus or 6 sulfur as 1 molecule. So they are still elements because they are made of one kind of things only. Okay. Now let's see number 3. Compounds consists of molecules or ions. So we have molecule. Molecule means there are more than one element. When they join up, they are not forming ions. Okay, the process of joining up hydrogen and oxygen does not involve the formation of ions. Of course, in details, you may see it later. Okay, so now for temporarily, I can just put it in this way. Molecule means no charge. No charge. Ion, you can see their charge. Their charge. What kind of charge can we see? Maybe when you look at K2O, you don't see any charge. K2O, they have charge actually. The K is K positive. The O is O2 minus. They have charge. They are ions and they have charge. So this one, they have charge. This one, no charge. Okay, so they're linked together without forming ions. This one, they're linked together, they join together by forming ions. Okay, now number 4, okay, we already discussed. Okay, let's see number 5. 3 types of particles that make up matter are atoms, molecule, and ions. So atom, molecule. Be careful with molecule. Molecule can be the element kind of molecule, can be the compound type of molecule. Okay, so molecule is under element and under compound. And then we have ions. Ions is under compound. Okay, so atoms are the simplest form of particle. We call it basic unit of matter. So atom. Okay, so basic unit, like C. Okay, 1 carbon atom. So it's just a basic unit. Okay, so how are we going to take it? Physically, it looks like this. Carbon atom. So it looks like 1 ball, something like that. Molecule, maybe H2, look like 2 balls join up. Okay. Molecule, H2O, it look like 2 small balls and 1 big ball, something like that. Different kind of balls. You know. Ions, ions is positive, negative, positive, for example. So something like this. Okay. So ions. Physically, you can see it by this simpler drawing. Atom, just 1 ball. Molecule, 2 same type of balls. Molecules under compound, different kind of ball, small ball and big balls. And then ions, they have charge, something like that. Okay, so all metals and some non-metals such as carbon is made up of 1 type of atom only. Metals, for example, iron metal. So iron, metals make up iron atom only. So molecules are combinations of 2 or more similar or different non-metal atoms. So to form molecule, they must be non-metal. They can be the same kind of atoms. Okay, like this. They are under element. There can be different kind of elements. They are under compound. Okay. Molecule substances such as bromine, Br2. This is element. Iodine, I2, so element, and oxygen, O2, element again, consists of molecules. Okay. Ions are formed when a neutral atom accepts or donates electrons. Okay, so they involve the donations of electrons. So for example, potassium donates electrons and become K positive. They give away their negative charge, so they become positive charge. And then oxygen receive electrons and become oxides. So oxygens receive electrons and become negatively charged. Okay, so the idea is like that. Huh? Okay, now example, sodium chloride. Okay, sodium chloride. I will slowly write down the formula one by one. So sodium Na plus, chloride Cl minus. So they are ion. Lead 2 bromide, Pb2 plus, ion. Bromide, Br minus, 2 of them, bromide. Okay, so they are ions again. Okay, now let's move on. Melting point and freezing point. Okay, so melting point is the constant temperature when a substance changes from solid state to liquid state at a specific pressure. Okay, so for example, melting point for ice is 0 degrees Celsius. 0 degrees Celsius. So this happens at the atmospheric pressure. Okay, so if you go to the moon, you want to melt the ice, the temperature is not, the melting point is not 0 degrees Celsius anymore. So it depends on the atmospheric pressure or the surrounding pressure. So different surrounding pressure, the melting point will be different. Okay, freezing point just the same as the melting point. It's just that melting point is solid to liquid, but freezing point is liquid to solid. Okay, freezing point for ice is still the same, 0 degrees Celsius. Different substances have different melting and freezing points. Okay, so like for example, the melting point for ice is 0 degrees Celsius, and then the melting point for carbon dioxide is much lower, it's negative value. Okay, so activity 2.1 is carried out to determine the melting and freezing points of naphthalene. So do you know what is naphthalene? Have you heard before?
Heard before, but don't know what is it.
It's the white color balls where we use it to chase away the cockroach. You know, maybe you put some in the wardrobe, so something like this, naphthalene. Okay, let's see. Naphthalene. So have you seen before this kind of white color balls? Yes, okay, so to chase away the cockroaches, so naphthalene. Okay, so you can easily buy it from anywhere. For example, like grocery shop. Okay, you can buy it. You take the naphthalene, it's a ball, and then you want to determine the melting point or the freezing point of naphthalene. Okay, so how we do it? So you look at the picture first. So this is the picture. We put naphthalene in the boiling tube, and then the boiling tube is put in the water bath, then only we heat up the water. Okay, we heat up the water. We don't straight away heat up the naphthalene, we heat up the water, and then the water heat up the naphthalene. So of course the reason that we do so is we want to heat it up evenly. If you heat up naphthalene straight away, maybe the bottom is very hot, but the top is not that hot, then that is not heating up evenly. So that's why we put everything in water, and then the water will heat up the naphthalene from all directions. So we call it heating it up evenly. Then of course we have thermometer there to check at what temperature it melts. Okay, so let's see. Material, naphthalene powder C10H8. This is the formula for naphthalene. It makes of 10 carbon and 8 hydrogen. Water. So material is the chemicals. Okay. Apparatus is not chemicals. So for example, like boiling tube, beakers, retort stand with clamp. So you see they use it here, retort stand with clamp, Bunsen burner, tripod stand, wire gauze, stopwatch to see how long it boils, Okay, so the procedure: naphthalene powder C10H8 is put into a boiling tube to about 4 cm in height. Okay, so you know when you buy this from grocery shop or maybe from a hardware shop, the naphthalene is ball shaped, so you break it down or you smash it, change it to powder. A thermometer is placed in the boiling tube, so something like this. The thermometer measure the temperature of naphthalene. The boiling tube is then clamped onto a retort stand and immersed into the water in the beaker, immersed in water. So we call this water bath. Water bath. Okay. Now number 4. The water in the beaker is first heated to 60 degrees Celsius. Then the water is heated more slowly. So we quickly heat it up to 60 degrees Celsius because we know that naphthalene, the boiling point is like around 80. Okay, it's around 80. So we don't want to heat it up slowly from room temperature to 60 degrees Celsius. It will take a lot of time. So we heat quickly to 60. Now we start to slow down because we know it is going to melt soon. So naphthalene is stirred continuously using the thermometer. I use thermometer to stir. The temperature of naphthalene is recorded every 30 seconds in the table 2.3 until the temperature reaches 90 degrees Celsius. Okay, so you will see something like this. You look at the graph. Yes, from room temperature, maybe from 60 degrees Celsius. So you continue to record your temperature. So every 30 seconds, you read the thermometer and write down the temperature. Then you draw the graph. So you will realize something like this. When it melts, right, it takes a long time to remain at the melting point before the temperature continue to increase. So it takes a long time, remain at the melting point. So of course, we need to know the reason. Of course, we will discuss this after a while. Okay. Now, the temperature of naphthalene is recorded every 30 seconds in table 2.3 until the temperature reaches 90 degrees Celsius. 90 degrees Celsius, finish melting already. So when the temperature exceeds 90 degrees Celsius, the boiling tube with its content is removed from the beaker. That means you take out the boiling tube and put like this. Let it cool down. Liquid naphthalene is left to cool another beaker as shown in another beaker as shown in diagram 2.4. Let it cool down, then we record down the temperature again. So then you will get a graph like this. So again, we have something similar. When it cooled down to its freezing point, which is 80 degrees Celsius, it takes a long time, a particular durations, for it to remain at this freezing point temperature, and it will continue to go down after a while. Okay, so after the freezing process finish, basically. So liquid naphthalene is stirred with the thermometer throughout the cooling process. Now let's see the discussion here. Okay. Oh, one more point up here. The temperature of liquid naphthalene is recorded every 30 seconds in table 2.4 until the temperature reaches 60 degrees Celsius. So basically we are doing this from 60 to 90, then 90 back to 60. Okay. Now let's see the discussion here. So discussion is explaining why something like this happens, you know. So now you see the explanation. The temperature of naphthalene does not change during melting. This is the melting point. Temperature does not change, remain at 80 degrees Celsius. So we need to know the reason. So this is because the heat energy supplied is absorbed to overcome the forces of attraction between naphthalene molecule until solid changes to liquid. Okay, so this is important. Okay, so the heat energy that you supply is used to break down the force of attraction. Okay, so in normal situation, right, the heat energy is either used to increase the kinetic energy of the particle, or is used to break down the force of attraction. So that is how they use the heat, the energy. So if they use the heat energy to increase the kinetic energy of the particles, that means the particle is moving faster and faster. So for this situation, if they use the heat in this way, then the temperature of the substance will increase. Temperature will increase. If they use the heat to break down the force of attraction, then the temperature remain constant. So I call this A, I call this B. Okay, so it happens here. A happens here, B happens here, and A again happens here. So again, A happens here. Okay, this is the other way around. So I should put it in the opposite way then. Okay, so it's the other way around. The other way around we discuss after a while. Okay, let's continue first. Number 2, naphthalene needs to be stirred continuously throughout the activity to ensure even heating. So even heating, that means you have to heat up the naphthalene evenly. Evenly means must be balanced. So you stir so that the part which is hot can mix with the part which is cold. Okay, so imagine you are stirring the naphthalene. Maybe the side is very hot because of the water, and then you stir the middle of the naphthalene, maybe not that hot. You stir, then the middle part becomes same temperature with the side. So that is what we call even heating. A hot water bath is used when heating the solid naphthalene to make sure heating temperature is uniform. We don't want direct heating. Direct heating will just heat up the bottoms very much. So we use water bath so that temperature is uniform. Okay, number 4. You see, discussion is explaining the reason why you do like this and why you do like that and so on. You know, so why you use water bath. Okay, why the temperature is not increasing. Why you need to stir continuously. You know, so it's explaining on why. You know, so number 4. The temperature of naphthalene does not change during freezing. Here, freezing, remain at 80 degrees Celsius for a particular moment. So this is because the heat energy lost to the surrounding is balanced by the heat energy released during the formation of forces of attraction between naphthalene molecule until liquid changes to solid. So what are they talking about? You see, during freezing, solid change to liquid change to solid. During freezing, liquid change to solid. And when liquid change to solid, forces of attraction is formed. When forces of attraction is formed, heat is released. Heat is released. Okay, so because heat is released, it avoids temperature from going down. Because heat is released, so the temperature will remain at the same temperature. It will not go down for temporarily. The surrounding is very cold, the surrounding may be room temperature 25 degrees Celsius, but the temperature will remain at this temperature at 80 degrees Celsius for a while because heat is released to maintain the temperature. Then it is not going down for temporarily until they form solid already. Then they don't form force of attraction anymore, then they don't release heat anymore, then the temperature will continue to go down. So the important word is there. Heat energy lost to the surrounding. Heat energy lost to the surrounding is balanced by heat energy released during formation of forces of attraction. So that's the thing. Okay, now let's continue. Next page. Okay, number 5. Let's see. Liquid naphthalene must be stirred and placed in a beaker for slow and uniform cooling effect. Otherwise, supercooling may take place. So you put the naphthalene in beaker. If you still remember just now, this is the boiling tube, and then you put them in beaker. Okay, so to let it cool down slowly. If you don't put in beaker, right, so it will have supercooling effect. Supercooling effect is like they are cooling too fast until it's lower than the freezing point, and then after that they come up again, and then they freeze. Supercooling may happen. Okay, so that's why you have to use a beaker. Okay, a beaker to avoid maybe the wind from the aircon from blowing to the naphthalene, or maybe the cold air to make it cold too fast. So the boiling point of naphthalene is 120 degrees Celsius. If solid naphthalene is heated directly without using a hot water bath, naphthalene may sublime. Sublime means solid change to gas, solid change to vapor straight away. Change to vapor. So vapor means the gas form that are flammable and poisonous. So that's why they had to use water bath because to avoid naphthalene to become vapor, and when it become vapor, it will become a poisonous gas. And flammable means can catch fire easily. So conclusion, the melting point of naphthalene is the same as the freezing point of naphthalene, that is 80 degrees Celsius. Okay, so finish the experiment. Okay, now let's see the graph in details. Okay, so our graph here. heating and cooling curve of naphthalene. Okay. Diagram 2.8 shows the analysis and interpretation of the heating curve of naphthalene. So you can see from 60 degrees Celsius, let's say, you heat up the naphthalene. Okay, then at 80 degrees Celsius it start to boil. Okay, so you record down the time. The time M1 is where it start to boil. Okay, so you see stage A here. The particle absorb heat energy. The kinetic energy increases. So you see this part very important. The heat energy absorbed is used to increase the kinetic energy. So just now I mentioned, when you increase the kinetic energy, the temperature increases. So and the particle vibrate faster, the temperature increases. So you see that there is a relationship between kinetic energy and temperature. When you increase kinetic energy, then you increase the temperature. It happens here. Okay, so until the melting point, so at time M1, naphthalene start to melt. And when they start to melt, of course, they become liquid. And we have a mixture of solid and liquid because they are in the process of melting. So at now they are in stage B. So let's see stage B. The temperature of naphthalene remains constant at 80 degrees Celsius. This is because the heat energy supply is absorbed to overcome the force of attraction between molecules or the particles until solid changes to liquid. So they remain at the same temperature. And what is the reason? Because the heat energy absorbed is not used to increase the kinetic energy at this moment. It is used to overcome or to break down the forces of attraction between the solid. Okay, so that's why just now I wrote down the heat can be used to increase kinetic energy. The heat can be used to break down the forces of attraction. So when you use the heat to break down the forces of attraction, temperature is not changing. Okay, so now at M2, naphthalene melts completely and becomes liquid. And then the liquid continues to heat up. So the particle absorbs heat energy, the kinetic energy increases. And the particle moves faster, the temperature increases. Okay, so again you can see the heat is now used to increase the kinetic energy, and because of that temperature increases. Okay, so make sure you get the very important point here. Increase of kinetic energy, temperature increase. Okay, break forces of attraction, temperature is constant. So these two are the two important concepts in this graph. Okay, now let's see number 2. So now we have to cool down the naphthalene. Okay, so from liquid, stage D. The particle lose heat energy, the kinetic energy decreases, and the particle moves slower, the temperature decreases. So you see the concept is the other way around. When they lose energy and it makes the kinetic energy decreases, that means the particles are moving slower, so then temperature will decrease. So you see temperature decrease when kinetic energy decrease. Okay, now decrease until this temperature it start to freeze. So at time M3, liquid naphthalene start to solidify. That means freeze. Okay, so they freeze, so they form solid. The temperature of naphthalene remains constant at 80 degrees Celsius. This is because the heat energy lost to the surrounding is balanced by the heat energy released during the formation of the force of attraction between molecules. So the particles come closer together to form solid. Okay, so what are they trying to say is the surrounding is very cold. the particle keep giving energy to the surrounding, or energy keep losing to the surrounding. But at the same time, they form forces of attraction, which release energy. And this energy is balanced with the energy that lost to the surrounding. And because of that, temperature remain constant because of that. Okay, so try to imagine it in terms of diagram. So let's say this is naphthalene. Naphthalene is here. Okay, so we have I draw a diagram to let you see. Energy is released to the surrounding. Okay, because of the formation of the forces of attraction. At the same time, energy is lost to the surrounding because the surrounding is very cold. So we have two processes here, one in blue color, one in green color. Okay, so energy loss, blue color is formation of forces of attraction that give out energy from the naphthalene molecules. So the heat energy is released because of the formation of the forces of attraction. And then at the same time, energy is lost to the surrounding. This is the green color arrow. Okay, so this heat energy is balanced with that heat energy, and because of that, temperature remain the same. So blue is formation of forces of attraction and heat releases. The green one, the surrounding is cold and energy lost to the surrounding. So the green one balanced with the blue one, and hence temperature remain. Okay, then never ever say about kinetic energy at this stage. Kinetic energy will make temperature go down. Okay, so now finish the freezing. Now it becomes solid at this point. At time M4, liquid naphthalene solidifies completely. Then it continue to drop in temperature. So you can see stage F. The particle continue to lose heat energy. The kinetic energy decreases, and the particle moves slower until they are closer to each other. The temperature decreases. So always remember, kinetic energy is directly related to temperature. If this kinetic energy go down, then temperature go down. Okay, so finish already. 2.1. Okay. Okay. Now, okay. 2.2, the development of the atomic model. Okay, so that means we want to find out how they find atoms to be like this. Okay, so to be like this. So atom look like this. So atom look like this. So of course it take a long ways to get to know this. Okay, so first, subatomic particles. Subatomic particle means the particles inside the atoms. So we have electrons, which is part of the atoms. We have protons. We also have neutrons. Okay, so subatomic particle means electron, protons, and neutrons. So an atom is made up of three types of subatomic particle, which are protons, neutrons, and electrons. So you can see proton and neutron stay in the nucleus, in the middle here. Okay, so nucleus contains proton and neutrons. So you can see proton is positively charged. The charge of one proton is positive 1. Neutron, the charge is 0. Okay, the charge is 0 for neutron. Okay, so electron is outside of the nucleus, is surrounding the nucleus. Electrons. So the charge of electron is negative 1. Okay, so 1 electron, the charge is negative 1. Of course, 2 electron, then negative 2, you know. So number 2. Okay.
And what is the second one?
The second one, you mean the negative 2 that I said just now?
No, the second round.
Oh, the second round is also electron. The first round there are 2 electrons, and then the second round you can see 1 electron here. So whenever they are on the round or the orbit, so we call them electrons. The things on the round here are electrons. Okay, so at the same time, let's take a closer look. The protons are the one in dark color. This one, I put it in blue. So you can see 3 protons. You know, 3 proton means the total charge is positive 3. So 3 protons, so the charge is positive 3. And then we also have 3 electrons. As you can see, they are on the round. 1 electron, 2 electron, and 3 electrons. So 3 electrons. So I put it in red. 1, 2, 3. Okay, 3 electrons. The charge is negative 3. Negative 3, yeah. Okay, so the positive charge and the negative charge is just nice to cancel off. Positive 3 minus 3 becomes 0. And because of that, end up with 0. So atom is neutral, no charge. Atom is neutral. Okay, now let's see number 2. In a neutral atom, number of positive charges equal to number of negative charges. Positive charges is due to protons. Negative charges is due to electrons. So since you have 3 protons and 3 electrons, so their charge is equal and hence cancel off. They are opposite sign, no? Positive and negative, then cancel off. Therefore, number of protons is equal to number of electrons. Okay, so that is a concept, no? A concept about the number of proton and electrons. Okay, now we have the history. Okay, so history, is it important? They ask also sometimes in objective questions. Developments of the atomic structures model. How they know atom look like that, you know, like having proton and neutron in the middle and electron in the surrounding. How they know? Okay, they take a long process to get to know that. So at the beginning, John Dalton, at this year, he said atom is just a ball. So he said matter is made up of a tiny particles called atoms. Just a ball. An atom is the smallest spherical body that cannot be created, destroyed, or indivisible. You cannot create atom, you cannot destroy atom, you cannot divide it into 2 pieces, for example. You cannot do so, based on John Dalton. At the end, of course, they realize, we can break down atom in nuclear energy. in nuclear reactions, in nuclear physics, in other words, atom can be broken down to two smaller atoms. It happens. Okay, so that's why this old theory is at the end found to be not true already. The next, yes.
Need to memorize.
What to remember is, you just try to remember something like this. John Dalton, the picture is like this. You remember the picture, you know. This point, try your best. If you can remember, of course, it's better. If you cannot remember, it's okay. Just remember the name of the scientist and how it looks like, a ball shape. So the details, if you can remember, that is the best. If you cannot, just leave it. All atoms of an element are the same. That means if iron, then all of them are ball of this size. All of them are the ball of this size. If let's say copper, then it is a slightly bigger or maybe slightly smaller ball. Okay, different size. J.J. Thomson, the second scientist. These scientists say that atom is like this, look like this, having electrons. He discovered electrons already. Atom contains electrons that are negatively charged particles. Okay, so have dots that are electrons. Electrons are spread throughout the sphere-shaped atom, which is positively charged. So they say it to be like that, like a ball with black dots on it. The ball is positively charged. The black dot on the surface is negatively charged. Okay, then the third scientist, Ernest Rutherford. Now, this scientist, he discovered the nucleus. He said there is a positively charged nucleus, and in the nucleus there are protons. The electrons is negatively charged. Okay, so the electrons form electron cloud. Electron cloud is regions with electrons. Okay, so this region, this electron cloud is surrounding the nucleus. A big portions of the atoms consist of empty space. That means nucleus is just a small little part of the whole atom with matter, with things inside there, and the surrounding are quite empty and quite big, and it just occupied with some small little electrons. So electrons move outside the nucleus. So just remember the pictures. Okay, now let's move on. Niels Bohr. Okay, so this scientist, he discovered the electrons which is actually moving around in the fixed shells. So he discovered shell. Okay, so move in a shell. So just like the planet revolve around the sun in the solar system. So there's a similarities between the solar system and the atoms. Okay, and then James Chadwick, he discovered neutrons. He said the nucleus contains proton and neutrons. I have neutron there. Mass of neutron is almost the same as the mass of protons. Neutron contribute almost half of the mass of an atom. Okay, so this is the model that we use until now. Okay, so now that is their finding, and we just make use of it straight away. Okay, now let's see 2.3 atomic structures, proton number and nucleon number. Proton number is the number of proton in the nucleus of an atom. That means how many protons. Okay, so for a neutral atom, the number of proton and the number of electrons are the same. This one important. Atom is neutral. If they are not neutral, we call it ion. You know, so atom is neutral, and atoms has the same number of proton with electrons, so that the charge can balance off. Nucleon number is the total number of proton and neutrons in the nucleus of an atom. Okay, so that means nucleon number is proton plus neutron. This one is just proton. Okay, so that's why you can see down here they put an equation saying that nucleon number equal to number of proton plus number of neutrons. Okay, example. State the proton number of the atom. So you can see 2p, 2 proton, 2 neutron, 2 electrons. Okay, they ask for proton number. So proton number is 2. Proton number equal to 2, because 2p is written there. 2p. So because of this 2p, so it's 2 protons. Okay, example again. A potassium atom has 19 protons and 20 neutrons. What is the proton number and nucleon number of the atom? So the proton number is equal to the number of proton, right, which is 19. The nucleon number, so remember nucleon number, we need to add up the proton and the neutrons. So we get 39. Okay, so let's move on. Table 2.5 shows the relationship between subatomic particles and its proton and nucleon numbers. Okay, so the first relationship, number of neutrons. You want to find neutrons, right? You take nucleon number minus proton number. So you want to find nucleon number, you add up number of protons and number of neutrons. The third relationship, you know, atoms is neutral. Because of that, the number of protons is equal to the number of electrons. So we have 3 relationships. So you can see example here. Sodium, 11 proton, 11 electron. You see, same. Neutron is 12. So because of that, proton plus neutron, you get nucleon number 23. 11 plus 12 to get 23. Okay, so proton number, take this number of protons. So the idea is like that. Take proton plus neutron, add up, and then you get 23. Okay. So let's see example 2.3. The nucleon number of sodium atom is 23. Nucleon number 23. Sodium atom has 11 proton. Calculate the number of electrons. Okay, so we need to know that number of electrons is equal to number of proton. Same. So that is 11. Okay. So the question wants us to count the number of neutron also. So number of neutron. So as you can see just now, number of neutrons equal to nucleon number minus proton number. Okay, so we just do it here. Number of neutron equal to nucleon number minus proton number, so equal to 12. Okay, so let's move on. Okay, so the next part is standard representation of an atom. Okay, so that means how we represent an atom. So you can see An atom can be represented using a standard representation as shown in diagram 2.12. 2.12. Okay, so this is the one. You want to represent an atom, so you put the element here, the symbol of an element. Then you put the nucleon number on top. You put the proton number at the bottom. So this is the standard representation of an atom. Okay, so example 2.4, you see, Al is the symbol of the element, which is aluminium. Aluminium. 27 is the nucleon number, 13 is the proton number. So you see, proton number is 13, nucleon number is 27, number of proton is also 13. State the number of neutrons. So to find the number of neutrons, we minus number of neutrons, you take nucleon number minus proton number, and then you get number of neutrons. And to find out the number of electrons, just remember the number of electrons is equal to the number of proton, which is 13. Okay, so I let you see something also. Okay, I put it down here. Have you heard before periodic table?
Yes.
Okay, let's see. Periodic table. Image. Okay, so let's say okay, I don't want this. Let's say this one. Okay, no, let's say this one. Okay, this one maybe still okay. Okay, maybe I use, okay, I type different keywords. Periodic table, SPM. Okay. So you will realize something like this. You realize, let's say for example, lithium. You can see lithium here. So the 3 and the 7. The 3, the smaller number, is the proton. The proton number. The proton number. The 7.0 is the nucleon. The nucleon number. Sometimes you may heard something else. You may heard of this as relative atomic mass. So for now, at this stage, I call it nucleon number. So the smaller number is proton number. The bigger number is nucleon number. So this is the symbol of the element. They don't follow the format sometimes. They don't follow this format where the 27 is on top, then the smaller number is at the bottom. No, this is left right. Okay, so sometimes it happens. So okay, let's continue. Atomic structures and electron arrangement. Atoms are made up of a nucleus and electrons that move around the nucleus in orbit known as shell. Okay, so that means the electrons is in the shells. The round here are called shells. Okay, so you see the first shell, 2 black dots on it, that means 2 electrons. The first shell fill a maximum of 2 electrons. The electron arrangement is very stable and is called a duplet electron arrangement. Duplet means 2. Okay, the first shell can take 2 electrons only, then it is known as full already. It's called duplet. The second shell, you see 2, 4, 6, 8 electrons. Fill a maximum of 8 electrons. The electron arrangement is very stable and is called an octet electron arrangement. The third shells, you can see 2, 4, 6, 8. Fill a maximum of 8 electrons. The electron arrangement is very stable and is called an octet electron arrangement. So you can see first shell 2 electrons, second shell maximum 8 electrons, third shell maximum 8 electrons. Okay, so valence electrons are electrons that occupy the outermost shell of an atom. So you look at the outermost shell, so 8 electrons here, then we say there are 8 valence electrons for this atom. Okay, so for example, okay, let's see. The proton number of calcium is 20. So therefore calcium atom has 20 electrons. You know, proton and electrons are the same. So to put 20 electrons in shells, so you have to put 2 in the first shell, then to put 8 in the second, then to put 8 again in the third, then you find out how many electrons remain. 2 remain, put in the fourth shell. So the electron arrangement is written as 2.8.8.2. So that is the electron arrangement. So you must memorize first shell 2, second shell 8, third shell 8, then the remaining put in the fourth. Okay, so elements with the same number of valence electrons have similar chemical properties. So for example, lithium has 2,1, sodium 2.8.1, potassium 2.8.8.1. The valence electrons is the last number. They all have 1 valence electron. 1 valence electrons. So they have similar chemical property. That means they have the same chemical reaction. Okay, so now an electron arrangement diagram shows the nucleus and electron arrangement of an atom. So this is the one, electron arrangement diagram. An atomic structure diagram shows the number of protons and neutrons in the nucleus and electron arrangement of an atom. Okay, so you can see different information for the atomic structure diagram. Okay, so atomic structure diagram, of course you will see on the next page. The difference between these two diagrams is on the next page. Okay, so let's say we go through a little bit. Okay, so let's see the pictures. So this is electron arrangement diagram. So you can see the nucleus and the electron arrangement. Nucleus, they just put there an A. Atomic structure, you can see the nucleus, they put proton, how many proton and how many neutrons. You can see the difference. So you can see here they put C, that is carbon. This one they put 6 proton and 6 neutrons. This one aluminium, 13 proton, 14 neutrons. Okay, so the structures, the diagram looks different. You get different information. So for example, you see sodium atom has 11 proton and 12 neutrons. You can get the information from this diagram, not from this. This one we don't know. From here we can't see. Electron arrangement is 2.8.1. You can get it from this as well as this. Number of valence electron is 1. This one, the outermost shell, 1 dot on it, 1 electrons. You can get from here as well. Okay, so carbons, you can see the information on your own. Aluminium also, So aluminum is 2.8.3, yeah? 2, 8 for the second shell and 3 electron for the third shell. Okay, then okay, so we will look at 2.4 next time. Okay, now I just leave it like this first.